So imagine a future, if you will, where we're in Lower Manhattan and it looks just like it does today. So this is a block just a few miles from here, but all these vehicles are electric. So this might be 10, 20, 30 years from now, but we've transitioned the transportation fleet to completely electric, and the cars look the exact same. Now there's still a problem. All of these vehicles need to be charged, and they're sitting idle for a significant amount of time. So say we start installing wireless chargers to charge just a few of them while they're sitting there. So these two vans down here, the drivers are inside making deliveries, and we've installed wireless chargers to recharge their batteries while they're sitting there. Next, we install chargers along these delivery zones for all these vehicles. So ambulances, taxis, police cars. Next, we think, well, when these vehicles are at the stoplight, they're also stopped, and we may be able to transfer power to them there. So now these 5 vehicles at the stoplight, for the 1, 2, 3 minutes they're stopped, their batteries are also being recharged. And eventually, all the vehicles on the road, even while they're moving, are being wirelessly powered with their batteries recharged by our ubiquitous wireless chargers. So the transportation future is one that's all electric. And you may argue whether that's 10 years, 20 years, 30 years away, whether you're coming from the GM side or the Tesla side. But Bloomberg's predicting that by 2040, 35% of our transportation fleet will be all electric. But today, actually, these electric vehicles aren't being adopted in the numbers that we're hoping. There's still nearly a perfect match between the subsidies, which are shown in the dark gray bars here, and the share of electric vehicles that make up new car registrations in those countries. And that's in large reason because of battery cost. So we need subsidies to make electric vehicles cost competitive with gas vehicles. The other major problem is that we need, according to Morgan Stanley, almost $3 trillion in infrastructure investment to make this happen. So this ranges from the utility side to the materials and mining side, but there's still over $1 trillion we need in just utility and infrastructure investment to make electric vehicles a reality. So how are we going to get there, and how are we going to charge these vehicles when they're on the road while also solving the issue of cost competitiveness for this electric fleet? So right now you might plug in your electric vehicle like this. Here's a Nissan Leaf, so pull up to a charge station, you put the plug in. But also in the future you might charge it kind of like we're starting to see some iPhone chargers now. So today you can go to Starbucks, plug in a wireless charger to your phone, which isn't the most elegant solution yet, and you place it on a pad and it's wirelessly recharged. And that same technology can be adopted for electric vehicles and is being adopted. So what is the promise of wireless charging or transferring energy without a connection? So in wired charging, obviously we have the length of a wire that the vehicle can move. So it's got to be stopped for that energy transfer to happen. But in wireless charging, there's starting to be academic demonstrations now. While the vehicle's driving, we can transfer energy to it. Secondly, someone needs to plug in the vehicle. So if we wanted to do this during deliveries or at stoplights, it's pretty much totally impractical for a driver to run out of their vehicle, plug it into a stoplight and get back in, and then unplug it to drive away. But with wirelessly charging, it automatically starts and stops at these stoplights. Lastly, wireless charging can be grid-friendly, where instead of having all of the EV charging concentrated at one location and one time of day, we can distribute it temporally and across the entire grid that already exists. And the key driver is that we can change the battery size of these electric vehicles from having to store all of the energy you need for one day to a much smaller fraction of that because the vehicles are being recharged as they're driving or traveling around a city. So that's the promise of wirelessly charging, but where are we at today? So here's your iPhone charger. It's about 25 watts. And then you can scale up. So there's a few companies building electric vehicle chargers in the 3 to 10 kilowatt range. And then there's some companies like Momentum that are building them for electric buses. And you're in the hundreds of kilowatt range because these buses have enormous battery packs. But the price goes up faster than the power does. So you can get an iPhone wireless charger for 10, 20, 30 bucks. Then you scale up and you're in the thousands of dollars. And then for these electric buses, you're in the hundreds of thousands of dollars. And that makes it not, you actually don't save money by reducing the battery pack size because of how expensive the wireless chargers are. And so just to kind of drive home these power numbers for you, if we had a Tesla, which all of us should once the price comes down a bit more, you can imagine that with that iPhone charger, it takes a year, so we're hopefully not going to use that for our electric vehicle unless we only want to drive it once a year. These standard ones are good for overnight, and then the bus ones, you could recharge a Tesla in under half an hour. And if you had your Tesla and instead of having it parked charging, you had it at a stoplight for 2 minutes, you could actually recharge the battery from 0.0004% for the iPhone, so we're still not interested in that. But at these hundreds of kilowatt power levels, we can actually get close to 10% of the battery recharged at a single stoplight. So as you drive, you could automatically get a meaningful recharge of your electric vehicle. So this is one reason why we don't see wireless chargers on the road everywhere. The power levels that give you a meaningful recharge are cost prohibitive. So to solve this, some of the OEMs have started coming to market with pads that you can place in your garage. And basically that means that wireless charging is just a luxury replacement for the plug you would have in your garage anyways. It's kind of like taking the technology where you could charge an airplane in mid-flight and making it into a gas station attendant. So instead of letting our airplanes fly farther, and with wireless charging it's automatic, we just put a gas station attendant in your garage so you don't have to plug in your electric vehicle. So how are we trying to address these twin problems of cost and the two-sided market? So on the cost side, the cost of these wireless chargers is driven by coil design. And at the frequency that people are building these, you need these two components called litz wire and a magnetic ferrite to achieve the efficiency that makes wireless charging feasible. So these two comprise 80% of the cost of a wireless power transfer system that's on the market today. And if you go to higher frequency, so take our switching frequency of the system up by an order of magnitude or two, there's the possibility that you can achieve the same performance but get rid of the litz wire and magnetic ferrite and drive down the cost. And that's our approach. So why doesn't everyone do it then? If you just kind of do what you're doing with these high powers, this is a 400 volt converter, your device is at the sun's surface temperature as soon as you get into the megahertz range. And that's what you need to eliminate litz wire. And if you're at the temperature of the surface of the sun, your converter's on fire and you're in trouble. So you have to use techniques, including new materials and new circuit techniques, to overcome these constraints and get into the frequency range where you can get good efficiency without the very expensive components. And that's what our lab is focused on. So this is one of the boards we've developed. This would be on the transmitting side. And this takes a DC input and outputs the high frequency AC that you would use to go across your air gap here. And so I have that. This is the first generation. This is what about the size of our second generation would look like without the components installed. And then on the vehicle side, and this is that board without the components installed, you have something to convert that high frequency AC back down to DC to charge the battery. And you guys can pass those around if you want. There's no IP that I think you can glean from the boards. So that's the prototype. This is our 500 watt, 13 megahertz prototype. And we've also built a 1 kilowatt, 6 megahertz prototype. So here's kind of where the field's at. If you look at, and this is 2015, so some people, including some ARPA-E programs, have started developing technology that breaks this barrier a bit. And if you look at frequency and power, so we need to be above 1 megahertz to get rid of litz wire, maybe above 2 or 3, depending on who you talk to, where litz wire starts becoming absolutely prohibitively expensive. And we want to be in this 10 to 100 kilowatt range to get power high enough to quickly recharge electric vehicles. So we're here today, which is about a 7x improvement over the state of the art with these two prototypes. So we have a long way to go, about 10x more in power to get into the range we want. But we're starting to push the boundaries of the field, and we're going to continue building that direction. So here are the simple specs on our prototype. So the BMW charger, which is coming to market next year, is about 3 kilowatts and about 85% DC to DC efficiency. So just with these simple prototypes, and again, our coils are just loops of wire. They have no magnetic components or litz wire in them. We can achieve similar efficiencies, and our goal now is to scale up the power to the 10 to 100 kilowatt range. So that's the cost side of it. How are we going to solve the two-sided market problem? The way we're going to do that is looking at commercial vehicles as our beachhead market. It's just not feasible to say, hey, New York City, I want to install chargers everywhere with an unproven technology and no customer. So my background is building commercial electric vehicles, and they're a great candidate for electrification. And the primary reason is they do a fixed known route every day. So whether this is a school bus, FedEx truck, a different delivery vehicle, something operating in a port, you never on Saturday decide, hey, I want to go visit grandma who lives 500 miles away and my EV can't get us there. And the other reason commercial vehicles are strong candidates for electrification is that their operators need to bring down, they have a long-term financial horizon, and they need to bring down their O&M costs directly to drive their bottom line. And that's kind of the promise of electric vehicles, that your fuel plus maintenance savings over the long term save you money, even with a higher upfront capital costs. And so there's a ton of different commercial vehicle markets. So what exactly are we looking at for this beachhead? Well, we need to look at people who have an economic incentive to go EV, not just people that want to go green. That doesn't really result in driving sales. And we also want to install both pads and have receivers on vehicles. So we'd like to just sell to one person that owns both the real estate and the vehicles. And then lastly, we're looking for places where commercial EVs have started to gain traction already, so that we're just proposing the wireless charging as new, not also the electrification. And the two prime candidates that we're looking at right now are ports, where we've started to see some electrification have strong mandates to electrify, and municipalities, where they're going to have a broad mix of electric vehicles that can all share the same charging system. So right now, so on Monday night, we actually got a $100,000 seed grant to develop the 10 kilowatt prototype. And in the next year or two, we're going to look to scale that up to 100 kilowatts. The other part of it is we have some EMI considerations with wireless charging, where the stray field's going, and I'm happy to talk about that more. But as we scale up in power, that's going to be important to nail down. And then right now, we're really focused on figuring out these beachhead markets and looking at who is going to be our initial pilot customers for this. So the revenue model, there's a bunch of ways we could approach this. And hardware, we might have to do for the pilots, but that's a tough business to be in. We want to be the utility of the 21st century. So to start, we want to be the gas station of the 21st century. We're going to buy power from the utility and sell it on a kilowatt hour transferred basis to our customers. But eventually, as this becomes more and more ubiquitous, we want to integrate distributed generation and storage with these wireless chargers and become the utility that provides the infrastructure for mass electrification. So the team that we're looking at, my background and with my PI, we're one expert, not me, and an aspiring expert in power electronics. And we're really focused on how do we make efficient inverters and rectifiers at high frequency. And then we've partnered with the Fan Lab, also at Stanford, and they're experts in electromagnetism. And so Peter's the other graduate student I'm working with, and John Fan leads that group. And then my background is in as a product manager at Motive Power Systems, bringing first of their kind commercial electric vehicles to market, including garbage trucks, school buses, and delivery vans. So our vision is to start with these ports and municipalities that have strong promises to move toward electrification or mandates. So just in New York City, imagine that all of these vehicles that are coming could share the same charge network. So what do we have coming up in New York City? These are promises or mandates or goals that I've put together. So 5,700 electric buses, 2,000 city-owned passenger EVs for employees, 1,500 UPS trucks, and we have $250 million that the governor just committed to charging infrastructure in the state. So those all could share the same network of charging pads in the city. And for ports, the Port of LA and Long Beach has 40% of US imports that go through it, and a strong push to electrify from the state for air quality standards. So they have all zero emissions by 2035 as a goal, 17,000 trucks there, and almost $1 billion California is committed to charging infrastructure in the state. So today, they've already started electrifying, and that is a huge signal to us. So they have a system that costs $13.5 million a mile to wirelessly recharge vehicles, and they're paying $250,000 per electric vehicle terminal truck. So we're aiming to build the infrastructure for the mass electrification of ports, municipalities, and all these adjacent markets. And I'd love to take questions or comments now.
Hi, Grayson. So it's a fascinating idea, and I'm really pleased to have heard it. You didn't mention space once.
Yeah.
What are you going to do for us?
So for space, so there's a few. So on kind of the practical side, wireless power transfer, actually a lot of our interest is from rugged environment applications where they want to replace cables that wear out with wireless power transfer coils, which have no contact. So we're looking at that kind of on the practical side. The second is that very high frequency converters are extremely power dense. So we'd love to partner on not necessarily wireless power transfer, but on the underlying technology for DC-DC converters. And then lastly, the long-term vision is as an enabling feature for electric flight.
So I was just in a mission study, or a study in which inductive charging was one of the highlighted technologies. Mm-hmm. So you and I should talk about that, because there's a couple other mission applications that I can think of.
Yeah, I'd love to hear more. You definitely would have a better idea of all the applications than I would. Thank you.
And
yeah.
So NASA's also about aeronautics, mm-hmm. and electrifying aircraft is something that we're advancing in order to reduce carbon emissions. So that's maybe an application.
Yeah.
So one of the things that it looks like you have a fabulous idea of how to disrupt the market, right? I mean, using delivery trucks that have to stop regularly and et cetera. In my head, I'm trying to figure out how much is it going to cost to install this kind of infrastructure? You're going to have to bring power underground, right, mm-hmm. to an element that will be parked over. And so there's a lot of concrete, wire, conduit, load analysis, et cetera. And so looking at all of that, I'm just curious about, like, what would it actually take? I know you mentioned $3 trillion, I think, but does that include all of those kind of impacts and all the policy issues associated with that?
Right. Yeah. So that's a great point, and I don't want to understate the infrastructure investment required. I think kind of our approach is that we have to make this investment anyways. So the difference between installing a wireless charger and a wired charger right next to the road is 2 feet of wire plus digging up the concrete and relaying it down. So that's kind of a big risk, I think, is that this infrastructure gets done before wireless charging is ready, and we just go wired. And then the switching cost is enormous. But that's a big reason why I think now is an important time, because we're about to invest in rewiring the entire grid in some way to support charging, whether it's wired or wireless. So you're totally right. And I think that we're focused on the incremental cost. If you add charging anyways, we don't think it's that onerous. Yeah.
How would the business model work once you deploy these chargers on public streets, for example? I mean, how do you charge individual car owners, for example?
Right, that's a great question. Yeah, and we haven't gotten exactly to it, but the charging system already has somewhat of a model for it where you could either go subscription based, you sign up and pay $100 a month for all your electricity covered, or we look to go like on a per kilowatt hour basis, and you'd obviously need some sort of communication between the car and the charger.
You kind of have to do that anyway, though, to recognize the position of the car.
Exactly.
So I'm curious about the anticipated kind of match between the life cycle of the infrastructure that you're like integrating this into,
Right.
and the device that you're making. Like how long lived is a wireless charging station going to be?
Yeah, that was one.
I hadn't thought about that. I don't see any big lifetime risks in terms of the electrical components. One of the main things that we're focusing on research-wise is how do we make these passively cooled so that we don't need fans or pumps, which are usually in power electronic systems the first things to fail. So I hadn't thought specifically about the lifetime. We've been thinking about that more from a system complexity and reliability of fans and pumps. But in terms of power electronic systems, they should last a while,
Okay.
I believe.
The GaN amps are going to fail, right? I mean, how reliable are the GaN amps that you're using? And
Yep.
I'm not convinced that they would last tens of years.
Right, yeah, that's a great point. So just to give a little background, the devices that we're using are new semiconductor technology, which enable us to go to higher frequency. And it's a major area of research. And I think I've actually only published on the reliability and non-idealities in GaN HEMPs. So we're definitely working with device manufacturers, and we're counting on both silicon carbide and GaN to be ready for prime time to make this a reality.
Silicon carbide is not going to operate at 13 megahertz.
Right, we built converters at 6.78 megahertz, and we have some at higher frequency that we haven't published, but you're right, the GaN is preferred at those frequencies.
So I have a question on your 10 kilowatt prototype. It's very exciting.
1 kilowatt prototype.
I'm sorry, but you said you got funding to do a 10 kilowatt.
Yes.
So what's going to be the area of that pad or that solution?
The wireless charging pad itself. We haven't started digging into it. I guess we're focused on basically that you can scale up a single turn, maybe with other coils to make that happen, but we haven't started investigating. So the area of the 1 kilowatt, the diameter is 27 centimeters.
So what is that for power density? Is that like 20 kilowatts per meter squared, or where are you with that? So there are solutions that are about 18
Right.
kilowatts per meter square. You brought up the ARPA-E funded project. We have something project that's doing not inductive coupling, but
Right.
capacitive coupling, and they achieved 50 kilowatts per meter squared.
Right.
And we're very excited about that, and I'd like to know, were you guys
Yes.
also using GaN amps?
Yeah, so that's a Freedy's group at Boulder. So I'm very familiar with their work. The capacitive one I love, but it's hard for me to see how that extends to uncontrolled environments because the safety risks are so much higher with capacitive than inductive. So if you think about that, our kind of IP, so to speak, is in high frequency, the natural place to go is capacitive because you actually increase power with frequency. But for me, looking at, okay, how do we scale this widely, the safety risks of capacitive were too much for me to want to pursue. So in terms of power density, I don't have a great answer for you because I'd have to do all that math in my head right now.
Okay, how about the efficiency of the power transfer?
Efficiency right now, we're at 84% with the 1 kilowatt, and that's DC to DC, so from the rectified grid.
Great, thank you.
Yeah.
And what is the expected distance of the wireless?
So right now, that one is 13 centimeters. So it basically, like, you can trade off efficiency with the two factors are how big you make your coil and the distance. So it seems like in the literature, like a fair comparison is like a 2-to-1. Your diameter is twice the distance. BMW's pad they're coming out with is 10-to-1, it looks like, from the initial specs, 80 centimeters, 8-centimeter gap. So there's some trade-offs. It kind of so ours is 13 centimeters right now, to give you a straight answer, but you have to look at it in the context of how big your coil is, because I could give you a longer distance, but I just have a bigger coil with the same efficiency.
Yeah, your efficiency is going to improve if you come to 8 centimeters.
Right.
12 centimeters seems to be the kind of the people.
Right. That's kind of, we're aiming to be kind of in that range.
How about dust and dirt? Does it affect it?
Dust and dirt shouldn't be a problem. It's really metallic objects is what you need to focus on for foreign object detection, because those, you basically have to induce a current. So the more conductive the object is, the more you have to worry about it. So
Iron filing spill would really kind of screw you.
that would be kind of a problem.
And also, like salt. You know, I mean, when we salt the streets in Cleveland when it's snowy. And so there are some corrosive, and we plow them. And
Yeah.
so the plows pick up any, like if you have a plate down, it's not unlikely that they'll pull it up, right? I mean, so
Yeah.
there's some, maybe we just don't do electric vehicles in Cleveland, but I don't.
I hope not. No, I hope
But it's
you
a
do.
thought, it's a thought about how do you make things, you know, impervious to the environment they're working in.
Exactly. And we, yeah, go ahead.
So why not target indoor environments like a factory space where you're charging
Forklifts.
Forklift, yes. So that's, we actually, our lab has worked quite a bit with Daihen, Japanese people, to bring that to automated guide vehicles, AGVs. But for me, it's just, I'm an electric vehicle guy, and I think that's where the big impact is. I think forklifts, like you see wireless charging actually coming to market in that. And I think it's going to be a reality there in the next few years. You know, you can go and see demos, but I want the bigger one. I'm more excited about electric vehicles. So
I hate to do this. I have a more mundane question. So
Yeah.
When you start to deploy this in a somewhat uncontrolled environment, like what is your strategy around making sure that there is a place to charge and that the vehicle happens to be in that place, right? So is it like dedicated loading zones? Like if you put it at a stoplight,
Right.
for instance, in your vision.
Yeah.
Holy smokes, I need a charge, but I'm not at the front of the stoplight. I'm
Right.
5 cars back.
Right.
How do you deal with that stuff?
Yeah, so I think for the commercial vehicles, you kind of have to start. That's why we want to start there. Is like, you know, here's like a colored pad on the road that you would, right, a loading zone, basically. And then to make the stoplights a reality, you basically have to have it ubiquitous everywhere. But then the long-term vision, and Matt from McKinsey kind of referred to this yesterday, is that you'd have this for autonomous vehicles. So when you have vehicle-vehicle communication, you have like a charging lane, say one lane, and when vehicles know they need to charge, they go to that lane. Or you vehicle-to-vehicle communication at stoplights, for if we still have stoplights then, where, you know, this vehicle needs to charge, it gets priority for the pad location. Hoverboards. Yep.
I think that for the road applications, the distance is going to be a real challenge from a safety perspective. So I would guess you would need 20 centimeters of clearance, you know, between the bottom of the vehicle and the road, unless you're moving something relative.
Right, yeah, I don't want, there's some people that are doing mechanical movement. I definitely think that's not the right direction. But yeah, you're right. You need something like 15, 20 centimeters to make it a reality.
Also, we have microphones on the left and right-hand side over here. And anybody in the back of the room that might have a question, you're welcome to ask as well. Grayson, thanks for your time.
Thank you, guys.